Okay, so we are talking about model selection, and so let me remind you, there's two aspects that we're looking at the time being. So first is we need a criteria for selecting which we consider to be the best model, and then today we're going to focus on some search strategies, and we'll start with some of the basic ones that have been very much part of classical statistics. Okay, so remember that model selection is the process of deciding which variables to include in our regression model. Okay, and so the context is we might have many possible predictors in our data set, and we want to choose a succinct subset of them that are best at describing the response. Okay, so remember there were two ingredients. So the first ingredient was the criteria, which is what we focused on last time. For example, we had an adjusted version of R squared, which captures the measures the amount of residual variance there is, as we showed the relationship last time. And then there's other criteria, for example, AIC, BIC. And then we also look at things like prediction error. So for example, mean squared prediction error. And there are others, okay? So we just listed some of the ones that have been historically important, recognizing that there's still a lot of statistical research that deals with these sorts of issues. Okay, so I will make a note here that for things like prediction error, we're going to look at this later in the context of using techniques like cross-validation. But for now, I want to look at these first three because we can actually calculate them quite conveniently from the output of R's linear model fitting function Ln. Okay, and the thing I want to remind you of here is that for all of these, so R squared adjusted, AIC, and BIC, the criteria explicitly involve a penalty term, which I touched on last time, explicitly penalizes having too many predictors. So if we're making the model unnecessarily complex, these criteria have a term in there, as we saw, that penalizes having too many parameters. Okay, so if I want to write that out, I would say explicitly penalizes unnecessarily complex models. What we mean by unnecessarily complex is if we throw in additional predictors that don't actually help explain the response, then we would prefer the simpler one. Okay, so we would prefer to take out the unnecessary variables. And so related to that is the philosophical idea of Occam's razor, which I mentioned last time as well. And so as applied to this context of statistical modeling, we want to avoid including unnecessary variables. So applying the principle that we prefer simpler models, they're easier to interpret, and they can actually have better performance because we're not trying to model noise or overfit, as the term we use. Okay, so don't include unnecessary variables that don't help explain the response. And of course, conversely, we also want to do a good job of including everything that is useful for predicting the response. So that's the goal and challenge of a good model selection method. One famous statistician, John Newman, once said, basically his idea was that with enough parameters, you can fit you can fit any response. And his famous quip was, with 4 parameters, you can draw an elephant. And if you add another parameter with 5 parameters, you can even wiggle its trunk. And the idea is that if we put enough parameters and enough variables, you can get the data. You can torture your data such that it will confess to anything, and you can fit pretty much anything if you have enough parameters. Brief mention to some more modern kinds of predictive tools. For example, some of you may have heard of deep learning. So one of the challenges in deep learning is it's very flexible. You can have tens of thousands of parameters, and you use algorithms to locate estimates of all those parameters. But you can have a case where you have a lot more parameters than the actual amount of data you have, and so without metrics to help prevent overfitting, you can have a model that fits really well on the response that you have to train on, but it can actually do very poorly when we actually use it in practice. It's a big fad now, AI, deep learning, and all these related methods. So overfitting can be particularly a problem the more parameters you have in the model. So that's true as a general principle. Okay, so for our purposes for now, we just need to remember that some of these classical criteria have penalty terms attached to help prevent this sort of overfitting problem. Okay, so along with the criteria, we need strategies to search for among the possible models that we can fit. Okay, so I'll call this the search strategy. So remember, these two go hand in hand. You need a search strategy to examine potential models, and then we need to evaluate them using a selected criteria. Okay, so this is what I'm going to spend some time talking about today. So search strategies among the space of possible models. Okay, and so as mentioned, we will use with a chosen criteria, or singular form, any chosen criterion. Okay, so this is the focus of today's lecture, and so I want to mention some of the basic strategies, and then I want to show you how to do all of this in R. Okay, so let's get started with strategies. Okay, so first one. Okay, so I alluded to this before. We can do, for example, a brute force approach. Okay, so we could fit so the simplest approach, which actually also ensures that we get the best answer possible, is we just fit all the possible regressions. Okay, and so in our context, so suppose we have P predictors, so with So at the end of last lecture, I counted for you, well, how many possible regressions are there? Well, actually, so there's, I'll rewrite that sum and recap it. So this is the number of possible regressions. Okay, so it's P choose J for all values of J from 0 to P. Okay, so why is that? Well, if you don't have any predictors, you have P choose 0 regressions, and you have P choose 1 regressions that involve one predictor, and then P choose 2 regressions that have 2 predictors in them, and so on. And so you could imagine all possible subsets. Well, that's this expression, which according to binomial theorem, this sums up to 2 to the P, as we said last time. So there's 2 to the P is the P predictors. That is the number of regressions to fit. Okay, so you have this many potential models. And so this grows very quickly. It grows to the power P. Okay, so another way to think of this number to the p is, well, you can think of, okay, there's p predictors, so you can also think of this from a purely combinatorics point of view. Since you have p predictors, each predictor can either be in the model or not in the model, right? So two choices, in or out. And so for each of the p predictors, each of them can be in or out, so you have 2 times 2 times 2 up to p times. Okay, so that's another way of seeing that indeed there are 2 to the p possible models to fit. Okay, so the main comment I want to make about just doing them all is that it does find it finds the optimal model among all possible linear regression models, but it might not be computationally feasible if you have many predictors. Okay, but may be computationally intensive or even not feasible, even with modern computing power, especially if you have number of predictors in the thousands. This would not be a feasible approach. There would be no way to test all of them in a reasonable amount of time, or infeasible if p is large. Okay, so because of this, this exhaustive search is not always practically possible. So there's been a whole lot of proposed ways of doing the best we can with a finite computational budget. Okay, so among all these following approaches that I'll describe, the key idea is that we want to find a useful or even a good model. With the caveat that it might not necessarily be the optimal one, but still useful. Okay, so we want to find good or useful model with in a reasonable amount of computational time. Reasonable computational time. Okay, and so I want to point out and emphasize, I say good because it's not necessarily going to be the optimum. We might not find the global best solution. Okay, so this is not necessarily optimal, but hopefully still good enough for understanding our data set and also for making predictions. Okay, and so along the lines of finding a good model, a common theme among many strategies, they focus on adding or removing one variable at a time. Okay, many strategies focus on adding or removing variables one at a time. Okay, and so it's sort of like a sequential process. So we can also say it's sequentially. Okay, and so I'm going to mention start with the two simplest ways of searching possible models by following this sort of strategy. Okay, so the first basic strategy is simply to start from an empty model and add one variable at a time. Okay, so I'm going to explain this first basic strategy, which is simply forward selection. Okay, so the first sort of strategy was just all possible. Okay, so now I'm going to talk about these faster strategies, but not necessarily give us the optimal model. Okay, so the first one is forward selection. Okay, so the basic idea is to add one start with an empty model and add one variable at a time. Okay, so I'm going to run through the steps and explain how this is done. Okay, so we start with the model with no predictors. Okay, so start with model. So it doesn't have any of the predictors, so we start basically the intercept model that has the intercept. Okay, so that's beta 0 here. Okay, and so we're going to add one variable at a time. Okay, so what we're going to do is we're going to scan the space of possible models where we go from the current model we had and we add one variable. Okay, so starting from a model with 0 predictors, we put in the first. So we're going to first put in the first predictor. Okay, so we're going to fit all possible regressions with one predictor. Okay, so we're assuming with p is number of predictors, so we're going to fit p simple linear regression models. Okay, and then each of them will have one predictor. Okay, so models. So specifically, we mean, okay, so you can fit y equals beta 0 intercept plus beta 1 x, let's call it xj. Okay, and then we're going to fit all of the models of this form with just one predictor in them. Okay, so we have p such models. So j goes from 1 to p. Okay, and so we're going to fit all these possible models with one predictor. There's p of them, and we're going to pick the best one of those p models. Okay, and so that's the first step. Okay, so we fitted all possible regressions with just one predictor. So that's p of them, and then we're going to take the one that has the best value of the criteria which we've chosen to use with our model selection procedure. Okay, so next we just pick the best of the p models with one predictor. Okay. Let's pick the best according to the chosen criterion. Okay, so this is why when we do a model selection process, we might be using BIC, or we could be using adjusted R-squared. Okay, so we're going to evaluate these p regressions using the criterion we chose. Criterion. Okay, and then we're going to add that predictor to the model. So add the best, add that predictor. Okay, so let's call it xj. Okay, to the model. Okay, and so now we have one variable in the model. Okay, so now the next step is to add the next one. Okay, so we basically repeat the process. Okay, so now we have one variable in the model, and then we have p minus 1 other variables. And so now we're going to test all possible regressions that have two variables, the one we already had, and then adding a second variable to the model. Okay, so now we're going to fit. So now we have p minus, in the second step, we have p minus 1 models to fit. Okay, so what's going to be in them? Well, it's going to have with containing xj, so the same xj we identified in the first step. Okay, and one other predictor, and another variable. Okay, so these are all the regression models that have two variables, xj and something else. Okay, and so if so now we have to see what actually happens to the criterion. So if none of the p-1 models actually improves the criteria, then we're done. Okay, so you can't do better than just having xj in the model according to our criteria, and then if none of these improve, and then we stop and we're finished. Otherwise, again, we take the best of the p-1 models, and then we add that as our second predictor into the model. Okay, so again, I'll pick best of the p-1. Okay, again, according to the criterion. And so now we add that variable. So now we have, okay, so now we have, that model will correspond to having two predictors, two variables in the model. Okay, so pretty straightforward procedure. Okay, so at each time you just test all the possible models that involve adding one more variable than what's currently in the model, and then once we add it, we fix that, and then we add one more variable. Okay, so we just repeat this process. Okay, so and so on, repeat until you cannot improve the criterion anymore, in which case we stop. Okay, so continue adding one variable at a time in this way until we can no longer improve the criterion. Until no more variables improve the criterion, and then we stop. Okay, and the best model, of course, is the one that had the best value of the criterion up to our stopping point. Okay, and so the final model is final model is the one with the best criterion when we stop. We stop and have finished the process. But okay, and specifically when we mean stop is when there's no further improvements. Okay, so that is forward selection. Okay, and so pretty simple procedure, and can be easily carried out. And it was one of the first procedures devised, very simple for doing model selection. And indeed, it has a much lower computational complexity than doing the all possible regressions approach. Okay, so let's just explain why that's the case. Okay, so we can say that this is so note that this is faster, or actually much faster than all possible regressions. Okay, so let's do a quick complexity, computational complexity analysis. Okay, so so how many models do we have to fit at most if we follow the forward selection procedure? Okay, so let's just count. Okay, so the number of models to fit. Okay, since maximum number of models to fit is, okay, so how many things are we fitting? Okay, so to add the first variable, we would fit p regressions. Okay, so the first one, and then to add our second variable, we'd be choosing among p minus 1 models. So we have to fit an additional p minus 1 models, and then once we have two variables in the model to test whether we want to add a third one, we have to evaluate p minus 2 regressions that have the two variables in the model plus the third one. Okay, so on. And then if we have to get all the way to the end, and it turns out we actually need every variable in the model, well, ultimately we go down to two possible regressions when we have two variables left, and then finally the last model with all the variables. Of course, in practice, we'll probably most likely stop somewhere along the process, but this is the maximum number of models that would be needed to be fit according to our forward selection stepwise procedure. Okay, so what does this add up to? Well, it's the sum of all numbers from 1 to p. So we know that sums up to p plus 1 over 2. And so we see the difference between the sequential procedure and the all regressions procedure. So this scales on the order of p squared. So it scales quadratically in p. Whereas if we were to test all possible regressions, that would scale 2 to the p. Okay, which is on the order of quadratic, so p squared versus 2 to the p for if we were to test all possible regressions. Okay, so it is much faster, but unfortunately, of course, it may not give us the best solution. Okay, you might miss a lot of models along the way that are never fitted, and so we hope that such a procedure, even though it's much faster, we hope it'll give us a reasonable solution, but there's no guarantee that will give us the best model, especially when p is large. Okay, so that's one basic sequential procedure, and so we can imagine that we can also come up with a kind of a parallel procedure, which instead of adding one variable to the model at a time, does the reverse. So it starts with a full model and starts taking variables away. Okay, and so that is the next basic strategy, which is aptly named backward elimination. Okay, so next one. So this is now the overall the third strategy I'm describing is backward elimination. Okay, and so start with, so this does the procedure in the reverse. So start with a model, with the full model of all predictors. Model that has all p predictors. Okay, and then we're going to do in stepwise fashion. We're going to take one variable away at a time until we get to the best model that has been found according to the procedure. Okay, so I can describe it in a very similar way. So we just in the reverse direction in which we proceed. Okay, and so so we start with everything. So now we're going to fit P models. Okay, so why is it P? Well, we have P predictors, and we take one of them away. So there's P such models. Okay, so the models that result from taking away from removing one variable. Okay, so from the regression. Okay, and so if you remove one variable, it means each of these possible regressions of these P have P minus 1 predictor. Each has P minus 1 variables. Okay, and so much like when we talked about forward, we now do the same thing except it's backwards. So now we just pick the best of the P models according to the criterion we choose, and then we eliminate that variable to criterion. Okay, and then we eliminate. Let's call it. Eliminate that variable that was removed. Let's call it xj from the model. Okay, and so now we've removed one, and so now in a similar way we now fit all possible models that remove xj and one other variable. Okay, so we fit. So now there's P minus 1 models that remove xj, so the same xj from the model, and one other variable, and one other variable from the model. And so we sequentially remove variables in this fashion. And one other variable. Okay. Okay, and so likewise, continue until removing additional variable does not improve the model criterion that we chose. Okay, so again, pretty straightforward. Just the reverse forward selection. Okay, so fit all models that remove xj, one other variable, and then pick best of the P minus 1 models, and so now we have two variables removed. And I should mention, of course, or stop if none improve criterion. Okay, so we either just keep going until there's no more improvement. if we reach the point where the criterion starts to get worse again, when we continue to remove, then we stop, just like in forward selection, we stop when the criterion no longer improves when we add an additional variable. Okay, and so computational complexity is the same as forward selection, because you can see we start again by fitting P models and then P minus 1. P models removing one predictor, and then P minus 1 models removing a second predictor, and so on. So at most, again, we're fitting an order P squared number of models. Okay, so same computational complexity as forward selection. Okay, and then the next one is simply to recognizing that, well, there's nothing that says we only need to go forward or only go backward. Well, why don't we combine the two? So that could help improve the space of possible models that are searched according to a sequential strategy. So that would allow us to both add and remove variables, because sometimes you might not recognize that a variable needs to be removed until something else is in there, and vice versa. Okay, so this will help expand our search space to some extent. Still consider a pretty basic strategy, and still, of course, no guarantee that we'll get the optimal solution, but it does include the benefits of both sequentially adding and removing variables. So this is number 4. So we'll call this forward and backwards. Okay, so this self-explanatory name, it just combines a forward step and a backwards step. Okay, and so this allows the same individual variables to be both added and removed. Okay, so this point, because it contrasts from forward selection, where once you add a variable into the model, it's going to stay in the final model, or you just keep adding one at a time. And then backward elimination, we remove a variable. Once it's removed, it's forever removed, okay, until we get to the final model. So by alternating forward and backward steps, so we might add a variable and then add another one, and then we might actually remove, for example, the first one when we do an elimination step. Okay, so let me describe this procedure. So we're going to start as in forward selection. Okay, and so we're going to add a variable, and then at the point, suppose we have k variables. Okay, so now we currently have let's say k variables in the model. Okay, so we're going to try two things. We're going to try a backward step. So our backward step is, well, I'm going to try removing one of these k variables. Okay, so we're going to fit k models. So each of them is going to have one less variable. So k models with k minus 1 variables. Okay, and then if any of these have a better criterion, okay, so we remove the one that improves the model the most. Okay, if any of these improve the criterion, then we remove the variable that remove the variable that gives the most improvement, just like as we would do in backward elimination. That improves, or I'll say improves the model the most. Okay, and so we're going to try a backward step, and then we're going to alternate and then do a forward step. Okay, so again, if we currently have k variables currently in the model, then we would fit. Okay, so how many models do we have that have k plus 1? Well, we have p minus k, right? So there are currently p minus k variables that are not in the model when we have k in it. Okay, so we're going to fit all of those models with one additional predictor. So there are p minus k models with k plus 1 variables. Okay, and then likewise, if any of these improves our model selection criterion, add the variable that improves the model the most. Okay, so it sort of combines the features of both the forward and backwards basic procedures. So those are some of the earliest stepwise, so-called stepwise selection methods. Okay, so these are. So as a note to wrap up this part, I will say that these are basic stepwise selection methods. And some most early used. So it's good to see them once, and they're very easy to implement because they are built into R, as I will show you in just a moment. But I will point out that these are basic stepwise methods to get a, as we said, a good or useful, hopefully good, well-performing model. Of course, there are many more sophisticated methods available. Okay, so just mention a few. So many other more sophisticated procedures available. So, for example, some stochastic search strategies. So the reason I point out stochastic is, well, because this procedure is deterministic, right? So every time I carry out forward selection on the same data set, if I run it twice, I mean, it necessarily has to give me the same answer and the same variables in the model because the procedure is deterministic, right? So there's other types of procedures that involve some stochastic search, in the sense that if we run it with different random seeds, we could actually end up with different models, and then we can pick the best of those, for instance. And then there's also different kinds of penalization methods. So a famous one, just to give you the name, is lasso. Okay, so there's a whole variety of methods that have been developed because we want to find the best possible variables to include, specifically when we're dealing with a big number of predictors. I should also mention that okay, so one other note. So implicitly, what we've been assuming all along here, so we've assumed that the number of observations that we have, okay, the number of observations is larger than the number of, in order to fit any of the regression models that we've talked about here, I mean, implicitly we need to have more data than higher number of observations than number of predictors. Otherwise, we cannot invert X transpose X. Else X transpose X is not invertible. Okay, so this is the so-called classic regression setting where we have more data points than predictors. Okay, but in some situations, especially probably a very common one is when we're dealing with, for example, genetic data. We have many genes, and so a number of and not nearly as many human subjects compared to the number of genes. Okay, so that's an example of a practical scenario where this would not be true. Okay, which is the classical regression setting. Okay, and so I just want to mention that. Okay, so more specialized methods needed. If the number of possible predictors is larger than our sample size. Okay, so that should be sufficient as a comment for now. Okay, so I want to pause here now and show you how to run these basic variable selection strategies and to calculate the basic model selection criteria in R. So we're going to head over there for a demo. So we may touch on some of these later, closer to the end of the course. If you have some time to look at a few of these more advanced topics, then we will revisit these ideas at that time. Okay, so I will rejoin you on the workstation in just a moment. Okay, so we are going to revisit the coffee data set. Okay, so if you remember, there were 10 predictors after accounting for the different method types, okay, which was one of the categorical predictors. Okay, so I'm going to show you these, again, the model selection criteria, so how to calculate them, and then we'll run through the four different basic procedures for variable selection that we've talked about today. Okay, so let's load it in, and we're gonna start by fitting the full model, and then I'll show you how to extract the criteria. So after we have fitted a model. Okay, so here's the full model. Let's take a quick look at the summary to remind ourselves of this data set. Okay, so we're trying to predict the flavor rating of the coffee based on a bunch of variables. So one of them was categorical, which was the method of processing. Okay, and then we have all these other continuous predictors, so aroma, aftertaste, and so on. Okay, so this is the full model that we have previously seen. Now, so once you have a fitted model, it's fairly simple to extract those three criteria I mentioned today: adjusted R squared, AIC, and BIC. Okay, so the adjusted R squared, as we see in this summary output, is actually printed out by R in this bottom part next to the R squared value. Okay, and so this gives it in this table format. If we want to extract the actual value, it's a property of the summary contained in the summary. So we can put adjusted R squared to get that exact value. So it's about 0.8073 here. Okay, so that's how we get adjusted R squared. We can also calculate AIC and BIC. Okay, those are to remind you, those are model selection criteria based on the likelihood function. And so remember, the least squares estimates are actually coincide with the MLE under our usual normal assumptions. Okay, so how to calculate AIC? Well, you simply put the name of the fitted model object inside the AIC function, and then it will calculate the value, so minus 1087. Okay, we can also do the same for BIC. Okay, and even before calculating, I know that BIC's value is going to be larger, so it'll be less negative. Okay, so it turns out to be about minus 1027. Okay, so what's the difference between AIC and BIC? Remember, both of them, as we mentioned last time, they penalize the number of predictors we put in the model. Okay, and for AIC, we add 2 to the AIC score every time we add a predictor to the model. So that's the amount of penalty for having a more complicated model. Okay, so the penalty in AIC is 2, okay, because it's 2 times Q, where Q is the number of parameters. Okay, on the other hand, BIC's penalty is the natural log, so ln of n, where n is the sample size. Okay, so for any reasonable sample size, in this case, I believe we have over 1,000 observations. So the natural log of 1,000 is much larger than 2. So therefore, BIC, as we mentioned, penalizes you for adding a variable more heavily and more strongly than in AIC. So therefore, the scores for BIC generally will be a little bit larger. Okay, so it's larger by a factor according to a log of the sample size. Okay, so that's how we get these 3 criteria from the basic model fit. All right, so the first strategy we looked at was all possible regressions. So R has a library that can do all that for us fairly automatically. Okay, so to do that, I'm going to use the library. The name is Leaps. Okay, so again, if you don't have it, you should install it first using install.packages. Okay, so let's load in the library, and so the key function that carries out this computation is the function reg subsets. Okay, and so it has quite a bit of detailed syntax. We can always look at the documentation for details. So let's go here. So oops. Okay, so functions for model selection, and so you can see it can handle a lot of the different strategies we talked about. They call it the exhaustive search, which is what we called all possible regression, and then there's backward, forward, and then sequential. Okay, and so in this case we have 10 predictors, and so we can tell it to literally consider all possible regressions. So that's why you have like 2 to the 10 possible regressions. So it's still manageable. It's about just over 1,000 possible regressions. It has this kind of funny argument. It's called really big. So if you have a lot of predictors and you actually want to exhaustively search, then we can explicitly tell the function to exhaustively search, recognizing that it could take quite a long time if p was quite a bit larger, right? If p was 50 or 100, it could take a very long time to actually calculate all the regressions. Okay, and so the syntax is pretty similar to how we specify regression formulas. Okay, so just by putting the dot here, it means that all possible columns will be used in this selection process. Okay, so let's go ahead and run this, and doesn't take very long in this case. Just over 1,000 regression models were fitted. Okay, so we can extract some things from it. So we can compute, for example, a summary. So we can take the summary of the output. Okay, and so you can just take a quick look at it. It has quite a number of attributes, and so in the summary, basically, okay. So let's scroll up here. So basically, it just tells us in each model which variables were included. Okay, so the very first model has one predictor. It's aftertaste. Okay, and then so on. So you notice the first 10 models each have one predictor. Okay, because we can make p possible models with one predictor. So this just shows which ones have which variable in them. Okay, and then it moves on to all the possible models with 2 predictors. So now you have 10 choose 2 possible models. So that goes down to 45 possible models with 2 predictors, and then it tells you which variables were in them. So this is how it exhaustively enumerates all the possible models. Okay, and so some of the useful attributes of this summary object is this which matrix, which tells us of all the 1,000 and some odd models, which variables are in each of those models. And then it also includes calculation of things like adjusted R squared and also BIC. Okay, so if I just do extract the adjusted R squared, it just lists all the possible R squareds in all the different models. And so for using adjusted R squared as my criteria, I can just pick the best one. Okay, and similarly, I can extract all the BIC values of all the possible models. And if I'm using BIC as my criteria, then I can pick the best one. Okay, so it's a lot of numbers, so let's visualize them a little bit. Okay, so there are 10 variables, so I'm gonna call that P. And then what I'm going to do here is I'm just going to plot all these values of adjusted R squared and BIC according to, let's do a quick visualization based on how many variables in a model. So as we showed, the first 10 choose 1 models are the ones with 1 predictor, okay, and then the next 10 choose 2 models are the ones with 2 predictors, and so on. And so I can organize it according to that. So I'm going to create a vector that lists for each of the models how many variables are in that model. So I'm going to put that in the vector k. Okay, so you see what's in there basically lists. So the first 10 values are 1. Okay, so I'm repeating the value 1 10 times. Then I'm repeating the value 2 45 times, and so on. Okay, so that's how I built this vector k. All right, and so reason I bring this up is we can see an additional built-in R command, which is to make box plots. Okay, so box plots are useful because they can show you the range of values for each group. So I'm going to treat each group here as the number of predictors. Okay, so what I'm doing here is I'm going to plot the values of adjusted R squared by, so again the tilde, the number of predictors. So it's going to create a plot with the boxes for each value of number of predictors k from 1 to 10, and so that's this plot command. Okay, and so you see how the adjusted R squared changes. So for example, with just among all the 10 models with just one predictor, the best you can do is about an adjusted R squared of just below 0.8, and then you can see how so all the possible models with 2 predictors have this range of R squared values and so on. So it does appear in this case that using most of the variables is helpful. That using most of the predictors is what gives us what looks like the higher values of adjusted R squared. Okay, and then here I just added a line because we know adjusted R squared is going to be between, in this case, it's between 0, 0, and 1. Those are the key boundaries. Although, as we saw from the formula for adjusted R squared, it's actually possible for it to be negative if we put in a lot of really bad predictors. Okay, so we can also do the same box plot for BIC. So I'm going to do the same thing with BIC. So now we're looking for the opposite trend. Remember, lower values of BIC are better because we're subtracting 2 times the log likelihood at the parameter estimates. Okay, so higher likelihood is better, therefore lower BIC is better. So again, according to BIC, the lower values do tend to have at least 5 or 6 predictors in the model. Okay, so that's quick visualization of to summarize the 1,000 and some odd possible regressions. Okay, so now let's actually choose the best model. Since in this case we have tested all of them, we can, for example, find what's the highest value of adjusted R squared. So we can take the max of that vector. Okay, so the highest R squared was 0.8075. And so corresponding with the max command, that R also has a which.max, which tells us which element in the vector has this value. Okay, so it turns out it's the 1013th element. Okay, and so we can store this value. So I'm going to call this the model with the best adjusted R squared is the 1013th model. Okay, and then likewise I can do the same for BIC. So now I'm looking for the model with the lowest BIC because lower is better. Okay, so the minimum BIC is minus 1793, and then again, which elements, so the index of the model is extracted by taking which.min. So this is best BIC. So it's the 638 element of that vector. Okay, so in this case, adjusted R squared as a criteria and BIC as a criteria choose very different models. Okay, and the reason I extracted these numbers, so the model with the best R squared and the model with the best BIC, is now I can go to the which matrix, which remember lists which predictors are in each model, and then I can extract the row corresponding to the one with the best adjusted R squared and the best BIC. Okay, so this will tell me which predictors are in the best R squared adjusted model. We notice that it has, so it's true if it's in the if that predictor is in the model and false otherwise. So notice that pretty much it chooses the model with all the predictors except for one. It takes out the level associated with the semi-washed category. Okay, so you notice here the wet variable is true, so therefore this is by setting semi-washed to be false. That's saying that the estimated difference in mean response between semi-washed and dry has been removed from the model, because this this variable would be the difference between dry and semi-wash. So this has been removed by according to the adjusted R squared criteria. Okay, and so let's fit these models. So what I'm going to do is just to make this more intuitive, I'll just define my own indicator. So I'll set a wet variable if the method is wet, and then I'll set this, a similar one for semi-washed. So then we have 2 indicators corresponding to the 3 methods, and then I'm going to remove this column processing method from the data matrix. So I'm going to set it to null because I've now coded indicators. So now this variable is redundant. So I'm just going to remove it. And then I'm going to now fit the models chosen by adjusted R squared and also by BIC. Okay, so let's first fit the model chosen by adjusted R squared. So I'm just following the list of variables in here. Okay, so I'm putting everything in. So I have the wet indicator, but I'm going to remove the semi indicator is not going to be in the model. So this is the model corresponding to the best adjusted R squared identified by the search through all possible regressions. Okay, so let's fit the model, and then again we can calculate all these quantities. Okay, so the adjusted R squared is indeed 0.8075, and then as we showed, we can also calculate the corresponding AICs and BIC. Okay, and likewise I can do the same for the best BIC model. So again, let's look at which variables were selected according to the BIC criteria. So BIC is, as we see here, is more conservative. Okay, so remember it penalizes model complexity more strongly. Okay, so it actually removes a lot more variables. Okay, so moisture is dropped from the model, uniformity is not in the model, balance is not in the model, and then similar to adjusted R squared, the category for semi is not in the model. Okay, so based on this information, I can fit the best BIC model. So I'll use everything that's true here. So wet, aroma, aftertaste, and so basically there are 6 variables here. So I fit the best BIC model, and likewise I can compute some summaries. So in fact, the adjusted R squared is not that much different. It's 0.8063, and then I can look at the corresponding AICs and BIC value. So of course, by construction, this is the lowest BIC value out of the 1024 models. Okay, and then we notice that it is about 10 BIC units better than the model chosen according to the adjusted R squared criteria. Okay, so key thing to note here is the model selection criterion does matter. Okay, so you can get depending on which criteria we choose, we can get different final models. Okay, so again, I do want to mention there is no one-size-fits-all approach to choosing a model selection criteria. That's why there are quite a few that are used in practice. Okay, so the last thing I want to show you is how we can do the same thing but with stepwise regression. So I'm going to again use a library for it. It's called mass, so I'll load the library. And to call the stepwise method, I'm going to define a full model, which is flavor with everything. Okay, so I'll just put a dot here, which symbolizes having all the predictors, using all the columns in the matrix other than the response, which is flavor. So call that the full model, and then call the empty model the one with just the intercept. Okay, so if I want to put just the intercept and no other predictors, then I explicitly need to type a 1 here. Okay, otherwise, if I do have predictors in the model, then the intercept will be included automatically. Okay, so those are full and empty models. And then the function using the mass package is the step AIC function. So the name of the function has AIC in it because AIC is the default criterion used. Okay, so the arguments use these full and empty models that I've defined here. So if I want to do forward selection, I want to start with the empty model, and then I want to search between the bounds of the empty model and the full model. So this just happens to be the syntax of it. So if I do stepwise using AIC. Then I just call it with the default argument for the penalty, which is so there's an argument for penalty, which is k. If I don't specify it, then we'll just use the AIC criterion, which is k equals 2. Okay, so penalty is 2 log likelihood units for each additional variable added to the model. Okay, so step AIC, so it will run through the steps of adding variables to the model. So if we go all the way down, we see that the final model selected actually had everything except for semi. Okay, so this is the same model that would have been selected by according to adjusted R squared. Okay, and so we scroll up, we can see each step that it encountered along the way. So we just walk you through that real quick. Okay, so it started with an empty model with just the intercept. Okay, so it fit the 10 possible regressions with each of these variables. Okay, so each of them are added to the model with just the intercept, and then it calculated the AIC so the AIC of the model with just aftertaste was minus 3923, and then so on. Okay, and so according to these 10 models with one predictor, it chose the best one, and that would have been aftertaste. That has the lowest AIC, so that was the model. That was the variable added in the first step of the forward selection. Okay, and so now we have a model with aftertaste, and now it fits the 9 possible models that have aftertaste plus one of these variables. Okay, so it adds all these possible models, and it calculates the AIC for each. And then there's also a none row, which corresponds to not adding anything else. Okay, so if none was the best, that means we would just simply stop. Okay, so that's how it's shown here. Okay, so it turns out adding acidity as a second variable improves AIC the most. Okay, so that's the variable that's added in the second step of forward selection. Okay, and then it proceeds, continues in the same fashion. So now we have 8 possible regressions with 3 variables, so 2 plus one of the remaining 8 variables, and then there's also the option of not adding anything. Okay, and then they have their corresponding AIC values, and then we continue in that fashion. And then it finally stopped at the end when, at the very last step, when adding semi into the model gives a worse AIC than stopping. Okay, so therefore it stopped, and so we end up with this final model. Okay, so we can do the same thing, but we can, for example, use BIC. So the penalty for BIC is to use log of the number of observations. So I can put that penalty explicitly. So by default, AIC sets k equals 2. I can use the step AIC function with a BIC criteria by setting k equals log n. So that's what I'm going to do here. So I'm going to do the same thing, but I'm going to use a BIC criterion. Okay, so if I run it, so we notice we get a different result with fewer variables. So in fact, this gives us 1, 2, 3, 4, 5, 6 variables, and I believe these are the same 6 variables that were found using the exhaustive approach with BIC as the criterion. Okay, so in this case, the forward stepwise gives us the same answer as the exhaustive search. So in this case, we don't have too many variables, and so forward selection actually gives us the same answer. So it gives us what turns out to be, in this case, the global optimum out of the 1024 models. Okay, so we see in this case, we added variables in this order. Okay, so first we added aftertaste, and then we added acidity, and then we added aroma, then we added body, sweetness, and then finally wet. And then after we had wet, we noticed that adding any of the 4 remaining variables does not improve the BIC. and therefore we have stopped. Okay, so I mean by programming design it still calls it AIC, but then we know that this is actually BIC because we have specified the penalty associated with BIC here. Okay, so at the very last step we stopped because all of these, adding any of the 4 remaining variables into the model gives a worse BIC than stopping. Therefore we stop and we have a final model with 6 predictors. Okay, and so we can fit the model, and then this is in fact the same model we had before, which is the one corresponding to the global best BIC. Okay, and then we can also use the same function to carry out backward elimination. So instead of setting direction equals 4, we set direction equals backward. Okay, and then it turns out we get the same model. Okay, so now we remove one variable at a time until we get to the model where we have these 6 variables. And then we notice that removing any of these 6 variables actually makes the BIC worse, and therefore we stop. And our final model has these 6 predictors. Okay, and then so in this case, forward and backward and exhaustive give us the same model. And then finally, we can do forward backward. So this does forward selection combined with backward elimination. So we put direction equals both. So you can see now at each step it considers all the possible regressions that. So for example, the last step, it looks at all the 4 possible regressions that add a 7th variable, and it also looks at the 6 possible regressions that remove one of the 6 variables. Okay, so that's why you have both the plus and the minus considered now at this step. Okay, and it turns out none of those 10 options improves the BIC, and therefore at the end we stop. Okay, so that illustrates how we can carry out these basic variable selection strategies in R using some built-in packages. Okay, so as a final note here, in this example, the 10 variables is a fairly small problem, and so all of these 3 stepwise approaches actually identify the same model using the BIC criterion, and it identifies the same global best model that we found by doing an exhaustive search through all possible regressions. Okay, so that's what I wanted to talk about today. I'll just pause for a moment, and if you have any questions, please ask me in chat, and I will answer them before signing off. Okay, so I don't see any questions for now, so we will be back on stream on Monday, and so don't forget to finish your assignment number 2, which is due Friday, and then I have office hours later this afternoon, and then also tomorrow morning. All right, so we will see you for the next lecture on Monday.